On a clear Tuesday morning in July of 1985, a group of geologists from the U.S. Geological Survey drove their truck to the edge of a barren, cracked lakebed in the California desert. They had instruments. They had clipboards. They had decades of combined scientific experience. What they did not have was any explanation for what they were about to find. Because sitting in the middle of that flat, lifeless expanse, in a place where there was no wind strong enough, no current, no human footprints, no animal tracks, no visible mechanism of any kind, were rocks. Hundreds of them. And they had moved. Some of them had traveled over 1,500 feet. Some had turned corners. Some had reversed direction entirely. One of them weighed over 700 pounds. Nobody saw it happen. No camera had captured it. No seismograph registered it. And in 40 years of scientific investigation, no one has been able to fully agree on why it keeps happening to this day. This is Racetrack, Playa, the most mysterious place in California. And the deeper you look, the stranger it gets. Before we talk about the rocks that move on their own, you need to understand what kind of place could even allow something like this to exist. Because Racetrack Playa isn't just remote. It isn't just strange. It is, by nearly every measure, one of the most hostile and inaccessible places in the continental United States. Death Valley National Park covers more than 5,200 square miles in the Mojave Desert, straddling the border of California and Nevada. It holds the record for the highest reliably recorded air temperature on Earth, 134 degrees Fahrenheit, logged in July of 1913. It sits at the lowest elevation in North America, nearly 280 feet below sea level at its deepest point, and it receives, on average, less than 2 inches of rain per year. Most people who visit Death Valley never make it to Racetrack Playa at all. To get there, you have to travel more than 27 miles on a road so rough, so jagged, so filled with sharp rocks, that it has been known to shred the tires of SUVs with no warning. There is no cell service. There is no gas station. There is no ranger station within reach. If something goes wrong out there, you are on your own. And somehow, in this place that nature itself seems to want you to avoid, there is a perfectly flat, perfectly oval ancient lakebed, roughly 2 miles long and 1 mile wide. That looks like something from another planet. The playa surface is cracked into a mosaic of dried mud polygons. It is perfectly white, blinding in the sun, completely flat to within a few inches across its entire length. And scattered across that ancient lakebed, sitting at the ends of long, shallow grooves carved into the mud, are the rocks. Some of those grooves stretch for hundreds of feet. Some curve gently. Some zigzag. Some run parallel to each other, then diverge. Some show rocks that traveled in the same direction as their neighbors, then turned sharply right while the others went left. And some of those grooves show a rock that traveled in one direction, stopped, reversed, and went back nearly the same way it came. The grooves are real. The rocks are real. The movement is real. But when the rocks move, nobody is ever there to see it. The rocks of Racetrack Playa were first documented by a man named Joseph Crook in 1915. He was a prospector, moving through Death Valley the way prospectors did, on foot, on mule, through heat and silence, and he came across the playa almost by accident. He noticed a large rock sitting at the end of a long furrow in the dried mud. He noted it in his journal. He had no explanation. He moved on. For the next several decades, the rocks were known only to the handful of prospectors, surveyors, and desert wanderers who occasionally passed through. It was not until the 1940s that anyone tried to study them scientifically. A government land surveyor named Jim McAllister became so fascinated by the moving rocks that he reported them to the U.S. Geological Survey. That report was largely ignored. It was a geologist named George Stanley who, in 1955, published the first serious academic paper on what he called sliding rocks. Stanley had spent time on the Playa, measured the grooves, cataloged the rocks, and tried to figure out what was happening. His conclusion: the rocks were being moved by some combination of wind and wet mud during the rare periods when the Playa flooded with a shallow sheet of water. The water would turn the cracked mud slippery, and then strong desert winds, gusts that could reach hurricane force through the mountain passes surrounding the Playa, would push the rocks slowly across the surface. On paper, it made sense. In practice, it raised more questions than it answered, because some of those rocks weigh over 700 pounds. To slide a 700-pound rock across mud, even very slippery mud, you would need sustained wind speeds of somewhere between 60 and 90 miles per hour, depending on the rock's surface area and the precise slickness of the mud. That kind of wind, blowing continuously for the minutes or hours it would take to move a rock hundreds of feet, would be catastrophic. It would be unmissable. It would certainly leave other evidence on the surface. But the only marks on the Playa surface were the grooves left by the rocks themselves. And that's not the strangest part. In 1968, two researchers named Robert Sharp and Dwight Carey launched what would become the most famous long-term study of the Racetrack Playa rocks. They arrived with a simple but elegant methodology. They selected 30 rocks. They named them, after women, alphabetically: Alberta, Betty, Carol. They drove stakes into the ground near each rock and measured its exact position relative to the stake. Then they walked away. They came back every year, sometimes twice a year, for 7 years. And over those 7 years, most of the rocks moved. Betty moved 212 feet in 1 year. Karen moved 157 feet. Some rocks barely moved at all. Some moved multiple times in different directions within a single year. And here is the finding that threw the entire wind theory into doubt. 2 rocks sitting less than a foot apart from each other, on the same flat surface, in presumably the same wind conditions, sometimes moved in completely different directions. Not slightly different directions, completely different. One rock might travel northeast, while its neighbor traveled southwest. One might curve right while the other went straight. If wind alone was the explanation, both rocks, sitting side by side, should have moved the same way. They did not. Sharp and Carey also discovered something even more unsettling. Some rocks disappeared entirely. Stakes were still in the ground. The grooves were still there, ending at the spot where the rock had sat for years. But the rock itself was gone. Where it went, nobody could say. Nobody ever found the missing rocks. After 7 years, Sharp and Carey published their results. The scientific community was fascinated. Nobody had a better explanation. The rocks, it seemed, were moving by some combination of factors that no one had yet managed to observe directly. Because in all those years of studying them, with all those check-in visits, no scientist had ever been present when a rock actually moved. The Playa seemed to know when people were watching. Theories multiplied through the 1970s and 1980s. And the more creative they got, the more they revealed just how stumped the scientific world actually was. The wind theory remained the most popular. Some researchers proposed that ice sheets forming on the Playa during cold desert nights might reduce friction so dramatically that even modest winds could push the rocks. Others suggested that the mud itself, when wet and thawing, could become a kind of lubricated surface that allowed rocks to travel on almost nothing. A researcher named Farouk Elbaz, who had worked with NASA on the Apollo moon missions, proposed something more radical. He suggested that the rocks were being moved not by surface conditions at all, but by microseismic activity. Tiny earthquakes, too small to be felt, too small to be recorded by most instruments, but powerful enough to send slow ripples through the waterlogged Playa surface. The rocks, he argued, were essentially surfing on invisible seismic waves. It was an extraordinary idea, and there was almost no evidence to support it. Death Valley is seismically active, there's no question about that. But the correlation between measurable seismic events and rock movement at Racetrack Playa had never been demonstrated. Others went even further. A geologist named John Reed proposed that the playa occasionally produced a phenomenon he called rafting, where sheets of ice, forming around the base of rocks during freezing desert nights and then expanding as they grew, could actually lift a rock slightly and carry it forward when the ice sheet tilted or shifted in the wind. The ice would melt by morning, leaving no trace. The rock would be in a new position with no explanation. It was elegant. It was creative. And for years, it was completely unproven. But here's what investigators discovered next, and it was even more shocking than the theories themselves. In 2006, a team of researchers set up a network of weather stations and time-lapse cameras around the playa. This was the most sophisticated monitoring effort the site had ever seen. The cameras would capture any movement. The weather stations would record every gust of wind, every temperature fluctuation, every barometric change. The cameras ran for 3 years. In 3 years of continuous monitoring, not a single rock was captured in motion. Think about that for a moment. The researchers hadn't arrived during a season when the rocks don't move. The grooves on the surface showed fresh activity. Rocks had clearly traveled during that period. But despite cameras covering significant portions of the playa, despite weather stations recording everything that happened meteorologically, the movement was never captured. The team published a paper in 2011 acknowledging their failure and arguing that the events likely happened during very specific, very brief windows, perhaps hours long at most, during which the exact combination of shallow flooding, freezing temperatures, wind, and mud consistency aligned to create the perfect conditions for movement. Those windows, they argued, were so rare and so brief that even 3 years of continuous monitoring had failed to catch one. It was the scientific equivalent of admitting that the phenomenon was almost impossibly difficult to observe, which is another way of saying, even with the best technology available, Racetrack Playa was still keeping it secret. And then came 2013, and everything changed. Richard Norris is a paleobiologist at the Scripps Institution of Oceanography. In late 2013, he and his cousin Jim Norris, along with a team of researchers, returned to Racetrack Playa with a new approach. Instead of trying to watch the entire playa, they focused on a small number of rocks. They installed motion-activated GPS loggers directly onto the rocks themselves, small, lightweight devices that would record position the moment the rock moved, with a timestamp accurate to the second. They also installed a weather station on the playa and set up time-lapse cameras. And then they waited. On December 20th, 2013, Richard Norris arrived at the playa at sunrise. And what he found stopped him in his tracks. The playa was flooded, covered in a shallow sheet of water, just a couple of inches deep. And across that sheet of water floated something he had never expected to see. Thin, transparent sheets of ice. The night had been cold enough to freeze the surface water into what he later described as window pane ice. Thin, fragile, but real. As the morning sun warmed the air, those ice sheets began to crack and shift. And when they did, driven by the lightest winds that Norris later described as gentle enough that he could barely feel them on his face, the ice sheets began to push against the rocks embedded in the playa surface. And the rocks moved. He watched it happen. For the first time in recorded human history, a scientist watched the sailing stones of Racetrack Playa actually sail. The GPS data confirmed what he saw. The rocks had been moving since early morning, creeping forward at speeds between 2 and 5 meters per minute, slow enough that you might miss the motion if you glanced away, but fast enough to travel hundreds of feet in a single session. The ice wasn't lifting the rocks. It was pushing them. A thin, expanding ice sheet, driven by the lightest desert wind, was transferring its momentum directly into the rocks at its leading edge. The scientific community celebrated. The mystery was solved. Headlines around the world announced that the sailing stones of Death Valley had finally been explained. But here's the thing nobody told you. The mystery wasn't solved at all. Read Norris's 2014 paper carefully, the one published in PLOS One that made international news, and you'll find something that almost no journalist bothered to mention. The ice shove hypothesis Norris documented in December 2013 explained some of the rock movements. The rocks he observed that morning moved in the same direction. They moved slowly. They moved in straight lines or gentle curves, consistent with the motion of a pushing ice sheet. But across the playa, there are grooves that show rocks making sharp right-angle turns. There are grooves that show rocks reversing direction entirely, not just curving back, but going back nearly the same way they came, with no obvious mechanism for an ice sheet to reverse. There are grooves made by rocks that moved alone, not in groups, with no parallel movement from neighboring rocks. And then there are the tracks that geologists like Paula Messina, who spent years mapping every groove on the playa using GPS technology, found simply inexplicable. In 1997, Messina published a comprehensive map of every visible track on the playa surface. Her analysis showed that individual rock tracks were so unique to each rock, so specific in their curves, their lengths, their directions, that they could not be explained by any single environmental mechanism acting uniformly across the playa. Some rocks appeared to be responding to a completely different force than their neighbors. Some tracks showed movements that would require winds from opposite directions in the same session. Some showed rocks that traveled when, by every meteorological record available, conditions should not have been sufficient for movement at all. Messina's conclusion was careful but clear. The sailing stones of Racetrack Playa were not the product of a single mechanism. They were the product of multiple different forces, acting at different times, in different combinations. A perfect storm so complex that it might never be fully replicated in a laboratory or fully observed in the field. The ice hypothesis explained one way rocks could move. It did not explain all the ways rocks have moved, and it certainly didn't explain what had been happening here for thousands of years before Richard Norris arrived with his GPS loggers. Because here is something the headlines definitely didn't tell you. Racetrack Playa is not just a geological curiosity. It is a place of enormous and largely uncatalogued prehistory. The playa and the surrounding Cottonwood and Last Chance mountain ranges show evidence of human habitation stretching back at least 10,000 years. The indigenous Timbisha Shoshone people, who have lived in Death Valley longer than any other human group, knew this place long before any geologist ever set foot on it. And according to the oral histories preserved by Timbisha elder Pauline Estevez and documented by anthropologists in the late 20th century, the moving rocks of the playa were known to the Timbisha for generations. They were not considered supernatural phenomena. They were not considered sacred, exactly. They were simply a feature of the landscape, something the desert did, the way the desert did many things that the modern world would later struggle to explain. The Timbisha called the area by a name that translates, roughly, to the place the rocks go walking. They had no explanation for why the rocks walked. They simply acknowledged that they did. Think about what that means. For at least 10,000 years, across thousands of human generations, This landscape has been doing something that our most advanced scientific instruments only partially explained in 2014. The first researcher to document the rocks did so in 1915. It took nearly 100 years after that for anyone to directly observe the movement. And even now, even with GPS and weather stations and time-lapse cameras, the full picture remains incomplete. This is where the story takes its darkest turn. In recent years, something has been happening to Racetrack Playa that worries researchers deeply. The Playa is changing. Climate change is altering the precipitation patterns of the Mojave Desert. The rare winter rains that historically flooded the Playa, creating the shallow sheets of water essential to ice formation and rock movement, are becoming even rarer. In some years, the Playa receives no significant water at all. In those years, the rocks don't move. But the rocks aren't the only problem. In 2016, the National Park Service released a report documenting significant visitor damage to Racetrack Playa. Despite the brutal road conditions, visitor numbers had climbed dramatically in the years following the 2014 media coverage of Norris's discovery. People were driving onto the Playa surface, something that is explicitly prohibited and has been for decades, and leaving tire tracks in the fragile dried mud. They were removing rocks. They were walking on grooves that had taken years, perhaps centuries, to form. Park rangers documented cases where visitors had moved rocks by hand, apparently wanting to participate in the mystery, to be part of it. Some rocks were found displaced to positions inconsistent with any natural movement. Their grooves, if they had any, pointed in directions that made no sense for the prevailing conditions. In other words, humans were now adding a completely uncontrollable variable to an environment that scientists were only just beginning to understand. The very publicity that came from solving part of the mystery was now threatening to erase the evidence needed to solve the rest of it. But that's not the most unsettling thing researchers have found. In 2019, a team of geologists conducting a remote sensing survey of the broader Death Valley region made an unexpected discovery. Using ground-penetrating radar and LiDAR scanning, a laser-based mapping technology capable of detecting features invisible to the naked eye, they mapped the subsurface structure of Racetrack Playa in detail no one had achieved before. What they found beneath the Playa's perfectly flat surface was extraordinary. The Playa sits in a graben, a sunken valley block created by fault movement, and beneath its hard, cracked surface lies a layer of sediment stretching back an estimated 65,000 years. That sediment tells the story of an ancient lake that once filled this basin, a lake that dried up and reformed multiple times over tens of thousands of years, each cycle leaving its own chemical signature in the mud. But embedded in those sediment layers, at depths corresponding to roughly 10,000 to 12,000 years ago, right at the edge of the last great ice age, the team found something that has not yet been fully explained, a layer of rock fragments, scattered across a wide area, showing orientation patterns inconsistent with water deposition. The fragments were not arranged the way sediment normally settles. They appeared to have been dragged or pushed laterally, as if moved by a force acting horizontally across the Playa surface, a force that moved rocks 10,000 years ago, before any human arrived to document them. The researchers published a preliminary note on the finding. A more complete study was promised. As of the most recent scientific literature available, that complete study has not yet appeared. What moved those ancient rocks? Was it the same mechanism that moves the rocks today? Was it something else entirely? Something connected to the enormous environmental upheaval at the end of the Ice Age that we haven't yet identified? Nobody knows. Let's talk about what Racetrack Playa has actually changed about our world. Because this isn't just a story about rocks sliding across a desert. This is a story about the limits of human certainty. For most of the 20th century, the scientific community operated on a fairly confident assumption that given enough time, enough instruments, and enough persistence, any natural phenomenon could be fully observed, measured, and explained. Racetrack Playa was a direct challenge to that assumption. For nearly 70 years, from Stanley's first paper in 1955 to the present day, the rocks resisted every attempt at complete explanation. What that resistance revealed is something that applies far beyond Death Valley. It revealed that nature is capable of producing highly complex, multivariable phenomena that defy simple mechanical explanations. Phenomena that can occur in the same place for thousands of years without following a single, consistent rule. It also changed how researchers approach desert environments. The Racetrack Playa studies contributed directly to the development of more nuanced models of aeolian, wind-driven processes in arid landscapes. They contributed to better understanding of how thin ice sheets behave in marginal climates. And they became a case study in the difficulty of studying low-frequency, high-impact natural events. Events that happen rarely but leave a dramatic record. The NASA Jet Propulsion Laboratory has cited the rock movement research in papers about surface processes on Mars. Because Mars has playas. Mars has dust and ice and wind. And there are features on the Martian surface that look, to some researchers, remarkably like the grooves of Racetrack Playa. If rocks can move on their own on Earth, in ways that took us a century to partially explain, what might be moving on Mars that we haven't even begun to understand? Here are some details about Racetrack Playa that almost never make it into the mainstream coverage. Details that, once you know them, make the place feel even stranger than the famous rocks. The playa is home to a single, large dolomite outcrop at its southern end called the Grandstand. Nobody has ever fully explained why the Grandstand exists where it does. Its geology is distinct from the surrounding mountains, and its age, as best as geologists can determine, suggests it may have been deposited during a catastrophic flood event far older than the most recent ice age. What kind of flood? From where? Nobody knows. The rocks on the playa come primarily from a dolomite outcrop on the cliffs to the south, and from a syenite formation to the northwest. Syenite is an igneous rock, dense, heavy, crystalline. It doesn't break off cliffs easily. How some of those rocks arrived at the playa, especially the very largest ones, has never been adequately explained by the gradual erosion models that researchers typically apply to the area. Paula Messina, in her exhaustive track mapping, found that several of the rocks showed track records suggesting they had been moving for decades, centuries, possibly, and that at least 2 rocks appeared to follow routes so consistent across multiple movement events that they seemed to be responding to the same topographic or magnetic features of the playa over and over again, returning to almost the same path even after moving and stopping and being repositioned by new movement, as if the rocks somehow remembered where they were going. And then there is the matter of the rocks that vanish. Sharp and Carey documented missing rocks during their 1968 to 1975 study. In subsequent years, other researchers have noted rocks whose tracks simply end, not at the edge of the playa, not against an obstacle, but in the middle of the open surface. The groove stops. The rock is gone. Where do they go? Some, presumably, are taken by visitors. But not all of the disappearances can be explained that way. Not all of them happened in eras when visitor traffic was significant. What happens to a rock whose groove simply ends in the middle of a flat, featureless, mile-wide lakebed? In the summer of 2022, a doctoral student named Maya Chun, working with a team from UC Riverside, began a new survey of Racetrack Playa using a combination of drone mapping and machine learning analysis of historical satellite imagery. The goal was to track rock movement events over a longer time period than any previous study had attempted, by analyzing subtle changes in the Playa surface visible from orbit. Her preliminary findings, presented at a geological conference in the fall of 2022, suggested something that surprised even veteran researchers. The movement events at Racetrack Playa appeared to occur in clusters, groups of events separated by years or even decades of relative stillness. And within those clusters, the pattern of movement seemed to suggest that certain rocks were consistently more mobile than others, not because of their weight or their shape, but because of their position on the playa. Certain spots on the playa surface, her analysis suggested, were movement hotspots. Rocks in those spots moved more often, more dramatically, and in more complex patterns than rocks in other areas. Rocks outside those hotspots barely moved at all, even during the same events. What was different about those spots? Was it the depth of the mud layer beneath them? Was it some subtle topographic feature invisible to the naked eye? Was it related to the subsurface structures found in the 2019 ground-penetrating radar survey? Chen's full analysis is ongoing. No final paper has been published. The hotspot phenomenon remains, for now, unexplained. And here is what makes this finding genuinely haunting. If certain spots on the playa are consistently more prone to movement than others, if the geography of the place itself is somehow channeling or amplifying the forces that move the rocks, then Racetrack Playa isn't just a place where interesting things happen randomly. It's a place with a structure we don't understand, following rules we haven't discovered, producing patterns we can only barely detect from space. It is, in every meaningful sense, still a mystery. There is one more thing you need to know about Racetrack Playa before we're done. One more layer that most people never get to. In 1987, a man named John Swan, a retired schoolteacher from Bakersfield, California, drove his truck out to the playa and spent 3 weeks camping there alone. He wasn't a scientist. He didn't have instruments. He just wanted to see, with his own eyes, whether a rock would move. For 3 weeks, he watched. He sat in his camp chair in the shade of his truck, and he watched the playa from sunup to sundown. He walked the surface every morning. He marked rocks with small cairns of pebbles and checked them every evening. Nothing moved. On the last day of his trip, the morning before he was supposed to leave, he woke up early, before dawn, and walked out onto the playa in the dark. And in the beam of his flashlight, at the edge of his marked rocks groove, a groove that had not changed in 3 weeks, he saw something that made him stop and stand still for a long time. The rock had moved. Not far, maybe 6 inches, but it had moved since the previous evening. In the dark, while he slept. He wrote about it in a letter to the National Park Service that is still in their archives. The letter ends with a single sentence that has stayed with me since I first read it. He wrote, "I watched for 3 weeks and I never saw it happen. But it did happen. And I think the lesson is that some things in this world keep their secrets not because they are supernatural, but because they are patient." Racetrack Playa has been patient for at least 10,000 years. Longer, perhaps, than we can accurately measure. Scientists have explained pieces of it. The ice hypothesis is real. The mud lubrication is real. The wind is real. But the whole picture, the full accounting of every groove, every missing rock, every movement event, every hot spot, every moment of stillness followed by inexplicable motion, that full picture remains just out of reach. And maybe that's the most important thing Racetrack Playa has to teach us. Not about rocks, not about ice or wind or mud, but about the nature of knowledge itself. We are very good at explaining the things we can see. We are much less good at explaining what happens in the dark, when no one is watching, in places so hostile and remote that observation itself becomes nearly impossible. The rocks are still out there right now. sitting at the ends of their grooves on a flat white lakebed in one of the most inhospitable places on the planet. And somewhere in the files of a PhD student in Riverside, in the archives of the National Park Service, in the unpublished data of a 2019 radar survey, in the oral histories of a people who have lived in that desert for 10,000 years, somewhere in all of that, might be the rest of the answer. Or maybe the rocks will keep walking long after we stop asking why. The question I keep coming back to is this. In a world where we have mapped the surface of Mars, sequenced the human genome, and built machines that can think, how is it that a few hundred rocks in a dry California lakebed can still move in ways we cannot fully explain? What else is out there doing the same?